Hello, in this video I'll be showing you how to solve equations that involve complex numbers. So I'll start off by talking about a very key property of two equal complex numbers, and then I've got two different examples for us to look at. And as always, I'll timestamp the different parts of this video below so you can just skip through to whichever part you want to see. If this video is useful, then please do like and subscribe. Before we answer a couple example questions, we first need to have a look at a really important property of complex numbers, which is, say we have two complex numbers, say z and w. Well, these two complex numbers are going to be equal to each other when we have their real parts being equal, so the real part of z is equal to the real part of w, and when their imaginary parts are equal, so the imaginary part of z is equal to the imaginary part of w. Okay, and this is a really important thing to understand. So our two complex numbers are going to be equal when their real parts are the same and their imaginary parts are the same. And this is going to be a really key thing to help us solve these equations. And initially this might seem like a really obvious statement to make. However, we could look at, say, fractions, for example. Well, just because we have two fractions being equal, say for example a over b is equal to c over d, well, this doesn't imply that their numerators are the same or their denominators are the same, because we could have, say, 1/2 is equal to 2 over 4. Okay, so it might seem like a really obvious statement to make, but actually if you think about other types of numbers, it doesn't necessarily mean that it's that obvious perhaps. So let's see how we can use this fact to answer some questions. So the first one we're going to look at is solving this equation here, where we have z squared is equal to 7 minus 24i, where z is just going to be some complex number we need to find. So how can we find a complex number such that when we square it, we get 7 minus 24i? Well, what we're going to do is say, well, if z is a complex number, okay, it could be expressed like this, a plus bi, where a and b are both real numbers. Because we know z can be written in this way, let's substitute that into this equation. And so we get a plus bi all squared is going to be equal to 7 minus 24i. Let's now expand the left hand side, and we're going to get a squared plus abi plus abi plus b squared I squared is equal to the right hand side of this equation. Well, now we can collect these two middle terms together. Hopefully you can see that. So we're going to get a squared plus 2abi plus, well, b squared multiplied by I squared. Well, I squared is -1. So really we've got b squared multiplied by -1, which is negative b squared. Okay, and that is also equal to our right hand side. Let's now put together the real and imaginary parts. So I've got a squared minus b squared plus 2abi is equal to 7 minus 24i. So let's think about what I said a minute ago. Our two complex numbers are equal when the real and imaginary parts are equal. So that must mean a squared plus minus b squared is equal to 7. And it also must mean 2abi is equal to -24. So let's write this out as a pair of equations that we now know to be true. So we know a squared minus b squared is equal to 7. And we know 2ab is equal to -24. So now we have a pair of simultaneous equations that we need to solve. So how could we solve these? Well, I'm going to use substitution. So I'm going to rearrange the second equation to make a the subject. So we get a is equal to -24 over 2b. And I'm then going to substitute that back into equation 1. So I've got -24 over 2b all squared minus b squared is equal to 7. Let me use my calculator. So 24 squared is 576. So we get 576 over 4b squared minus b squared is equal to 7. Let's multiply everything through by 4b squared, and we get 576 minus 4b to the power of 4 is equal to 28b squared. I'm now going to put all of my terms on the same side, and I get 0 is equal to 4b to the power of 4 plus 28b squared minus 576. And all of these terms are actually divisible by 4. So I get 0 is equal to b to the power of 4 plus 7b minus 144. Now, you could factorize this using your calculator, But if you're unsure how, you could actually rewrite this, and I'll use a different colour. We could say that, say, x is equal to b squared, and so this just becomes x squared plus 7x minus 144 is equal to 0. And so we could factorise this by saying that we could write it as x plus 16, x minus 9 is equal to 0. And so we're going to get x is equal to negative 16 or x is equal to 9. And so if we bring that over to our original quartic equation we had, then we have our solutions b squared are going to be equal to negative 16 or b squared is going to be equal to 9. Well, let's square root both sides and we get b is equal to plus or minus the square root of negative 16, or b is equal to plus or minus 3. Now, if we go right back to the start when I defined my complex number z, I said that a and b were both real numbers. Okay, and so we get b can't really be equal to plus or minus the square root of negative 16, as that would be an imaginary number, so I'm going to disregard this as a solution. Now, if you wanted to check this, you could actually calculate that as a solution and substitute it in, and you would actually get the same solutions as if we use this one here. However, there's no point because we'd just get a repeat of the answer, so we can ignore that complex solution. So let's focus in on b being plus or minus 3. So when we have b equal to 3, what I'm going to do is substitute it back in to one of our original equations. So I'm going to use this one here, okay, because this will then tell me my value of a. So if b is equal to 3, I get 2 lots of a times by 3 is equal to negative 24. And so I get 6a is equal to negative 24. And dividing both sides by 6, I get a is equal to negative 4. And so this gives me a solution of our complex number z being equal to negative 4 plus 3i. But let's not forget we also have when b is equal to negative 3. So let's substitute that in. We get 2 times a times negative 3 is equal to negative 24. And so we get negative 6a is negative 24. And dividing both sides by negative 6, we get a is equal to positive 4 this time. And so we get another solution for z being 4 minus 3i. And those will be our two solutions to this equation. Let's now take a look at a second example question here, where we have to solve 4z plus z conjugate is equal to 10 minus 18i. Now to do this, we're going to do the same sort of thing. I'm going to first define z to be equal to a plus bi, where a and b are both real numbers. So let's now substitute this in. So I've got 4 times z, so 4 times a plus bi, plus its conjugate, which is just a minus bi, is equal to 10 minus 18i. So let's now expand this left-hand side and we get 4a plus 4bi plus a minus bi is equal to 10 minus 18i. And so collecting like terms together, we get 5a plus 3bi is equal to 10 minus 18i. And because these two complex numbers are equal, we know their real parts are equal. So I know that 5a must be equal to 10, and so a must be equal to 2. And I also know 3b must be equal to negative 18. And so dividing both sides by 3, I get that b must be equal to negative 6. And so this gives me a solution for z, which is equal to 2 minus 6i. So hopefully this video was useful. If it was, please do like and subscribe, and go over to my channel where I have loads of other maths tutorials. Thanks for watching.